Welcome to the next lecture in Math 1342, Elementary Statistics at Dallas College with Professor Bailey. In 6.1, we're going to use a probability density curve to describe a population. We're going to use a normal curve to describe a normal population, convert values from a normal distribution to z-scores, find areas under the normal curve, and find the value from a normal distribution corresponding to a given proportion. We're going to put these all in context of a statistical study or why we use them and what this provides. So the first thing we're looking at is a continuous random variable. Consider a data set consisting of vehicle emissions. We can visualize these data with a relative frequency histogram, which you see on the right. Class intervals are chosen so that each rectangle represents a reasonably large number of vehicles. But vehicle emissions is a continuous random variable. Recall that a continuous variable is one whose possible values can be any value in some interval. So instead of just being 1, 2, 3, or integers or whole numbers, a continuous variable is, you think of it with decimal places. So between 0 and 1, there are an infinite number of possibilities as long as we keep moving the decimal place out. Suppose that the sample of vehicles was very large, consisting of millions. Because the amount of emissions is a continuous variable, there would be a reasonably large number of vehicles for each rectangle, even for smaller classes. You can see in the original one, we had one class for all emissions between 0 and 1. Here, we have, it looks like about 10 classes between 0 and 1. And so you get a better idea of the shape of the data with this, smaller groupings of responses. Such a histogram would look smooth and could be approximated by a curve, assuming there's millions of data points. The curve used to describe the distribution of this is called a probability density curve. It's called this because it tells what proportion of the data falls within a given interval. So remember that proportion and probability values can be thought of interchangeably. So if 10% of the data falls within a certain interval, then the probability of picking a random subject and being in that interval is also 0.1 or 10%. The area under a probability density curve between two values A and B, in this example below, or between 3 and 4, represent the proportion of a population whose values are between A and B. So again, you can see that the shaded area, the proportion of the population with values between 3 and 4, is equal to the area, which in this case is 0.17. You could also kind of think of this as that 17% of the respondents have a value or responded with a data point that is between 3 and 4, depending upon what this is. So again, note the proportion and the probability are represented by this area, the area under the probability density curve. It can also be interpreted, like I said, the probability can be interpreted from that proportion. This is really a mathematical concept, and when you pick one value, one point, if you will, in math, a point doesn't have any area. So, or I guess in this case, you could think of it, it has no width. And if you're thinking about the area like we saw in that rectangle in the last one, because this has no width, and like the rectangle would be width times length, then there is no area there. So what this is leading to is that we can't use the probability density curves to find a probability for one specific value, etc. So if x is a continuous random variable, the probability x equals one specific value will always equal 0. And again, this is more of a mathematical concept about one point in space or time or whatnot. Notice this also means that the probability that our data point is between A and B, non-inclusive, is equal to our point being between A and B, including the values of A and B. And that's just because, again, the point has no additional value, no probability or proportion, so it doesn't matter if you exclude it or include it. And so this all works from the idea that the area under the entire probability density curve is equal to 1. So really what we're doing a proportion of the curve and using like a percent value. So 20% between two values would give us a probability of 0.2. It would give us a proportion of 0.2 because 20% of the area is included between those two values. So see if you can answer these questions. Hit pause. This is pretty straightforward. Hit pause, answer these 4 questions, and then hit play again. Consider the probability density curve with some areas indicated. Find the proportion of the population between 0 and 1. Well, looking at the graph, we can see the area underneath the curve between 0 and 1 is 0.63, which represents the proportion, the probability, or even the percent of the area. And so the answer to number 1 is 0.63. The probability that a random selected value will be between 1 and 2. Again, we see here that the area under that interval between 1 and 2 is 0.23. That is our probability, just like it was the proportion in number 1, that these are kind of interchangeable. The proportion of the population between 0 and 2. Now we have 2 different areas that we have to combine. We're just going to add those together because that's the combined area, and the combined area represents the proportion or the probability, and so we get 0.86. The last question is a great question because it kind of gets you to kind of think about all of the information about a probability density curve. And so now we're looking at the probability that the value will be greater than 2. So this is the rest of the graph here, and we don't have a value for that area. So how do we solve this? Well, we know that the area under the total graph is equal to 1, so the area that's not shaded is going to be 1 minus the shaded area, which we calculated as 0.86. So 1 minus the area between 0 and 1 minus the area between 1 and 2 would give us 0.14, or 1 minus each of these values, or the total of their sum. A uniform distribution is one in which values in any region are equally likely. The probability density curve for a uniform distribution is a horizontal line. Imagine that when a traffic light turns red, it stays red for 30 seconds before turning green. If you pull up to the light when it is red, the amount of time you will wait before the light turns green is uniformly distributed between 0 and 30 seconds. So we can see that the bar goes here because it's a uniform distribution. Each answer, each possibility of waiting time has an equal likelihood. Okay? So we also know that the area under a probability density curve is equal to 1. And since we know that the responses are between 0 and 30, so the entire width is 30, we can calculate the height, because remember, 30 times x has to equal 1, So x equals 1 over 30. So let's try this one. Probabilities for the uniform distribution are straightforward. The probability of an event corresponds to the area of the rectangle, just like it did the area under the curve. This one's easier because we can easily calculate the area of a rectangle. So see if you can do this. Hit pause and calculate the probability that the waiting time is between 5 and 15 seconds. Hit pause and then hit play when you're ready. So again, we can see that the width of this rectangle is between 5 and 15, so that's 10 units. And we know the height is 1 over 30. So the area here, which represents the proportion, the probability, and the percent of possibilities, is all equal to the same thing. The width, 10, times the height, 1 over 30, or the area under the curve for a specific interval. And so we get that the probability that the waiting time is between 5 and 15 seconds is equal to the area of the rectangle we see shaded, and that is equal to 1/3. The quantity of the width, 10, times the height of the rectangle, 1 over 30. So we have another problem here. See if you can do this one. I don't have a graph for you here. I want you to draw that graph. It's very similar to the last one. The waiting time at a bus stop for the next bus to arrive is uniformly distributed between 0 and 10 minutes. See if you can draw the uniform distribution table and then calculate these probabilities. Okay, hit pause, draw your uniform distribution, and then solve these three problems. Hit pause now. Find the probability that the waiting time is less than 3 minutes. Well, we first have to draw our uniform distribution table. We know the x-axis is going to go between 0 and 10. And because that's 10 units wide, we know that the height of the rectangle will be 1 over 10. Okay? So when we look at this first problem, we find the probability the waiting time is less than 3 minutes. This is the width of that rectangle will be 3, and the top is 1 over 10, so 3 times 1 over 10. Find the probability that the waiting time is greater than 6 minutes. Well, greater than 6 minutes, the total is 10 minutes. 10 minus 6 gives us 4 minutes, so we're going to have 4 times 1 over 10, or 0.4. Find the probability that the waiting time is between 3 and 8 minutes. Well, 8 minus 3 is 5 minutes. And again, 5 times 1 over 10 gives me 0.5. Now we're going to look at normal curves, and this is a huge part of statistical analysis. Probability density curves come in many varieties depending on the characteristics of the populations they represent. Many important statistical procedures can be carried out using only one type of probability density curve called a normal curve. This is one of the most valuable tools, is using a normal curve if we can get our data, if our data does come in this kind of pattern of a bell-shaped diagram, if you will. Normal distributions have one mode, and the distributions are symmetric around the mode. Normal curves can extend infinitely far, both to the right and to the left. The population mean determines the location of the peak. Mean and median of a normal distribution are equal to the mode. Okay, so that's all mean, median, and mode are at this high point in these diagrams. Okay. The population standard deviations measures the spread of the population. Therefore, the normal curve is wide and flat when the standard deviation is large. You can see that here we're comparing two equal modes or means with different standard deviations. The second one is double the other. So the larger it is, the wider the data spreads out. The larger the standard deviation is, the shorter and fatter the data is going to be, or the diagram that represents the data. You can see here this skinny tall peak is a standard deviation of 1. This fatter curvy hill is a standard deviation of 2. Now, why is this important? Because we can use the empirical rule that we learned in a previous section to figure out the proportions. Remember that 99.7% of the data in a symmetrical or bell-shaped curve happens between the mean and 3 standard deviations, plus or minus 3 standard deviations. Within plus or minus 1, you get 68% of the data. 2 standard deviations, you get 95% of the data. And this works out so that we can make inferences about our data. So if we have a symmetrical data element, or symmetrical data distribution, that's what I want to say, then we can make some really great inferences about that. So this is kind of a proof. You don't need to do anything here except kind of listen. So this is just demonstrating a study. This is the body temperatures in a sample of 8,670 men. And the mean was calculated at 98.2, and the standard deviation was 0.6. Okay, so if we want to calculate and look at how much of the data is between 1, 2, and 3 standard deviations, we can easily calculate that. So for example, within 1 standard deviation, that's plus 0.6, which would give us 98.8, and minus 0.6, 1 standard deviation, minus 0.6 would give us 97.6. So if we look at the table over here, the data from 97.6 to 98.8 right here is the data that's within 1 standard deviation. If we look at that data here, add up all those values, we get 5,904, divide it by the total number in the population, and we can see that we actually got 68.1% of the data. So it shows you that the empirical rule is really close to accurate when we have a general normal curve, a bell-shaped curve, a symmetrical curve, roughly. You can tell that this information is not exactly symmetrical, and that's what's so valuable about this. If it just looks roughly symmetrical, then it tends to follow the empirical rule, and it allows us to know where most of the data is going to be. And so that's a powerful tool for making inference. Okay. We do not all know all the values in the population of body temperature measurements, but because the sample is bell-shaped, we approximate the population with a normal distribution, with mean equals 98.2 and standard deviation equals 0.6. The empirical rule demonstrates how areas under the curve represent proportions from the population. So here you can see the area under the curve is 0.68. 0.9 for 2 standard deviations, and 0.997 for 3. Again, you're probably getting tired of hearing this today. The area under the normal curve represents a proportion of the population, and this can be interpreted as a probability. It's therefore necessary to find areas under normal curves other than those specified by the empirical rule. I mean, we do know where those branches are at plus or minus 1, 2, or 3 standard deviations. But what if we want a smaller interval? And that's what this is talking about. How do I find the interval or the area for different intervals? So we're going to use the z-score. We found this before in a previous chapter, how to calculate this. And remember, the z-score just represents the data of the number of standard deviations above or below the mean or the mode. Okay. So remember that if it's a -1, it's 1 standard deviation below. If it's a +2, it's 2 standard deviations above the mean. So you're talking about plus is to the right of the center and minus is to the left of the center. Your book has a table of values we're going to look at in a minute. This is table A2. It's a good idea to print this z-score table. It makes a lot of calculations easier to do, and we're going to do some practices with this as well. So remember, the calculation of the z-score is the data value that you're looking at, one specific data value, minus the mean over the standard deviation. Okay. When we convert a data point that we observe to a z-score, this is called standardization. Okay, and if you're wanting some review, we covered this in section 3.3 earlier in the semester. So let's try one of these. Consider a woman whose height is 67 inches from a normal population with a mean of 64 inches and a standard deviation of 3 inches. So when we calculate the z-score, again, the observed value, 67, minus the mean, 64, over the standard deviation, which is 3 inches, and we get a value of 1. Okay? This means that the measurement height for a woman of 67 inches is 1 standard deviation above the mean. Okay? So the value of 67 from a normal population with a mean of 64 and a standard deviation of 3 corresponds to a z-score of 1 from a normal standard distribution. Okay? So try this. Compact fluorescent bulbs are more energy efficient than incandescent bulbs, but they take longer to reach brightness. The time that it takes for a compact fluorescent bulb to reach full brightness is normally distributed with mean 29.8 seconds and standard deviation 4.5 seconds. A randomly selected bulb takes 28 seconds to reach full brightness. Find and interpret the z-score for x equals 28. Again, hit pause, do the calculation, but then see if you can write a sentence which explains what that means. Okay, hit pause now. So when we plug these values in, our z-score is -0.4. A time of 28 seconds to reach full brightness is 0.4 standard deviations below the mean time of 29.8. Okay? Pretty straightforward. I hope you get that. A lot of what we do in statistics is take our numerical calculations and analysis and then put them in really clear and very, very specific language to avoid people misinterpreting what we're saying about the data. So this is what I was talking about. If you can, you might want to hit pause and go someplace to print table A2 because we're going to do some exercises with this. So table A2 is a z-score table, and what it allows us to do is to find the area to the left of any z-score. Okay, so you can see that if we look at the top row, we're looking at 0.00, right? And so this is when the z-score is actually equal to 0, this first value, which would be right here at the very center. Well, of course, if we're at the very center of a normal curve, then the area to the left will be half because the total area equals 1. And then we slowly move, in this case we're going to the right of the 0. How do I know that? Because these are all positive z-scores. These scores can be positive or negative. So as we go slowly to the right, we can see the area is growing. So the area as we go above the mean, we're going to start with an area at 0.5 at 0 and then go all the way up, or excuse me, get larger and larger till possibly we're at a value of 1. Okay? If we're looking for areas to the left of the mean, the z-score will be negative, and it'll start at 0.5 and then it'll go down until it's very close to 0. Okay? So here's an example. This represents, the table can be a little bit confusing. So this column represents, let's look at the 1, 2, 3, 4, 5th row, which is 0.04 is the z-score, and this is 0.400. So this is just 0.4. This is 0.41. When you add 0.01 to 0.4, you get 0.41. So this is getting us even closer little segments here. 0.42, 0.43, 0.44, 0.45, 0.46. Okay, so notice a z-score of 0.46 corresponds roughly to 67.72% of the data, or a proportion of 0.6772, which is roughly 68% of the data. The area is 0.6772, which we can see that's a probability of roughly, so a value of a z-score of less than or equal to this z-score would be this area, 0.6772, again representing roughly 68% of the data. Okay? So the column and the row headings are the z-score, and you add them together for 0.46. The data in the table is the area to the left of whatever z-score is the intersection of that point. So for example, here I'm circling 0.7389. This is the area to the left of 0.64. Alright. So see if you can find this. Hit pause and see if you can find this. Find the area to the left of z equals 1.26 using table A2. So this suggests you sketch a normal curve, label the point z equals 1.26, and shade in the area to the left of it. Obviously, most of us are not going to do that for every problem, but it's good at least as we start, because then we recognize, okay, the area is going to be greater than 1/2 because the z-score is positive, so I'm moving to the right of the center. If we look at table A2 and go down to the area for 1.26, that means we need to go, the columns have 1 decimal place, so we need to find the z-score of 1.2. That's this one right in the middle, okay? And then we need to go over to 0.6, so we get 1.26, and you can see that here that I've highlighted. Not sure why I highlighted 3 columns there, but anyway. So the value in the intersection of the row is 0.8962. This is the area to the left here. We have almost 90% of the data is below a z-score of 1.26. Okay. So let's see how we can use this a little more, specifically in probability and statistics. A study reported that the length of the pregnancy from conception to birth is approximately normally distributed with a mean of 272 days and a standard deviation of 9 days. What proportion of pregnancies last less than 259 days? Okay. Again, hit pause and see if you can calculate this and maybe use the table to find that area. Okay, so the first thing you have to do is calculate your z-score and then look on the table for that z-score. Hit pause now and try this. So our x value is 259, our mean is 272, our standard deviation is 9. We just plug in the values and we get a value of negative 1.44. which is what we'd expect, right? We'd expect this to be negative because we can see the mean here is 272. We're less than that, so it should be to the left of the mean, and the z-scores represent the standard deviations from the mean. So this is about 1.5, not quite 1.5 standard deviations less than the mean, okay? Now we need to find that negative 1.44. Again, we go to our table, go down to negative 1.44. The column is the single unit and then the tenths, 1 decimal place, negative 1.44, and we go over to 4.04. When we add those together, we get 1.44. And here we can see the area or proportion or probability is 0.0749. So the area to the left is 0.079. So approximately 7.5% of pregnancies last less than 250 days. To say this exactly, and it's not that much difference, we conclude that the proportion of pregnancies that last less than 259 days is 0.0749. Just a little more accurate than 7.5, but it's pretty much the same. 7.5%, excuse me. All right, try another one. Hit pause and see if you can do this. It's the same problem. Here we're asking what proportion of pregnancy lasts longer than 280 days. So when we calculate the z-score, we're expecting this to be positive. When we calculate that z-score, we get 0.89. Again, our x value is what we're looking at, the marker we're looking for, 280. We then go to our table. We're looking for 0.8 positive. Then we go over to 0.09. And we see the area is 0.8133. So we conclude that the proportion of pregnancies that last longer than 280 days is 0.1867. Wait, why was it not 0.8133? Oh, remember that the table A2 gives you the area to the left, the white area, and we want the area to the right, a value greater than, longer than 280 days. So in this case, once we have this value, we remember that the whole area under the curve equals 1. So this value represents the area to the left. So if we're looking for a value to the right or a value greater than that point, we have to subtract the table value from 1. When we subtract 1 minus 0.8133, we get 0.1867, and that's why we conclude that. Tricky, eh? Be mindful of this. And luckily the table A2 normally has an image of the normal curve with the area shaded to the left, so it reminds you. So now let's try another problem. Here we're going to try to figure out what proportion of pregnancies are full term, and the pregnancy is considered full term if it's between 252 days and 298 days. Again, hit pause and see if you can figure out how to do this when we're looking between two values. Okay. Hit pause now and try this. Well, we have two z-scores. We have to calculate those, right? And then we can find the area to the left. Well, notice what we're actually looking for. The area to the left of 298 is actually this total area to the left, including this little piece to the left of 252. So if we take the value from table A2 for 298 and subtract the value from table A2 for 252, which is just this little white triangle here, notice that we're getting the area between these 2 points. The area below 298 is everything to the end. And then we're subtracting out this little white piece at the end by using the area to the left of 252. Okay? So again, we're going to take the area to the left of 298, which is 2.89. That's interesting. On the area to the left of 252, which is equal to 0.0132, we subtract those, and we get the actual area between them. Okay, so it's the whole area to the left of 298, which was 2.89, minus the area to the left of 2.52, which is negative 2.22, and we see that roughly 98% of pregnancies, really almost 98.5, are full term. So that's a really high percentage. 98.5% of births are full term. So again, always remember that the back of your book provides technology examples and step-by-step instructions. This is for your TI-84 calculator, which you can use. I've left all the examples that are in the back. Why I did that, but I don't really go through these. These sections are very well written. They're brief, and they're instructional on how to solve these problems, either using a calculator or using Excel. Now, in my course, you do have to practice this. So the way that you learn the skills you need for the Excel homework is to go into the textbook and work through those problems and just open up Excel. In the book, I'm not sure if they give you access to the data set, which would be really anyway. So there's great examples in the book that will help you prepare for your exams and weeks and homework. All right. So see if you can do these. Try all of them, or if you want, just try that one. A normal population has mean and standard deviation of 3 and 1. Find the proportion of the population that is less than 1. So again, we're going to calculate the z-score, and then we're going to look in the table for that value. And on all of these, we're going to do the same. We're going to calculate the z-score. Now remember, in this case, because it's greater than, we calculate the z-score, find the area, and then subtract it from 1. Okay? And here we're looking for, this is all three cases. Now we have the last case when we're looking for the proportion between two values. So we find the area for the upper value, take the area and subtract the area for the lower value, and that gives us the difference between those two areas. All right. Now suppose we want to find the value from a normal distribution that has a given score. So we're trying to, like in this case, it's like, what is the data point that is exactly, let's say 1.2 units below the mean, okay? So we can use the standardization formula to calculate z given an x, and all we have to do, notice, is rewrite this equation when we're doing equations. So we want to solve this equation for x. If we do that, we multiply both sides by the standard deviation and get z times the standard deviation. Then we add u to it, and so you can see we have a simple formula to calculate a value of x that relates to a specific z-score, again, which is the distance above or below a number of standard deviations. So see if you can calculate this. Hit pause and try it. Heights in a group of men are normally distributed with mean mu equals 69 inches and a standard deviation sigma equals 3 inches. Find the height whose z-score is 0.6. This is really simple. This is a plug-and-play problem. So x equals the mean, 69, plus z, 0.6, times the standard deviation, 3. And so we get 70.8. We interpret this again. Remember, we always make simple sentences. A man 70.8 inches tall has a height 0.6 standard deviation above the mean. We know it's above because it's positive. All right. So how do we find the normal values? Again, sketch a curve. This is really just so you can think about positive being to the right of the center, negative being to the left. You can shade in. This may help you kind of visualize what you need to do, especially when you're using table values. If the area is on the right, subtract it from 1. This is what typically when you're looking for values greater than a specific value. Look in the body of table A2 to find the area closest. Sometimes the area will be exactly between 2 points. And so here, what we're trying to do here is, and I should have started with this, I'm sorry. You're given a proportion, like what, find a value where 30% of the data is below. So we would look for the value in the table that gives that area. 30% below would be 0.3 or 0.30, whatever. So we're looking at the data inside the A2 table. Once we find an entry that is 0.3000 or whatever, then we line up the column and row headings to find the z-score. And then, of course, we can obtain the data point by using that formula. The data point x equals the mean plus the z-score that we just that we found in the table times the standard deviation. We're going to try this problem now, so that may be a little bit confusing. Practice or experience always helps. Okay, see if you can do this. Hit pause and try it. And then if you're stuck, hit play a little bit, but if you get one part, maybe hit pause again. All right. Scores on an IQ test are normally distributed with a mean of 100 and a standard deviation of 15. Use Table A2 to answer the following. What score separates the upper 2% from the lower 98%? Okay. So we're looking for this score that separates the upper 2% from the area of the white, which is 98% or 0.98. Okay, the first thing we need to do is to find the area of the white triangle, the area to the left, because that's what table A2 has, and we know that is 0.98 or 1 minus 0.02. Now take your A2 table and look in the values in the table, not the title column and title rows. Look at the numbers inside the table and look until you find 0.98. Okay, 0.98. All right. If you do that, there is a value called 0.9798. And this corresponds, it's very close, you can see it. We're looking in the table, it's pretty close. This corresponds to a z-score of 2.05. When you find this data point, look over to the column heading and find out what the z-score is there. That would be 2.0, right, because it goes to the tenths. And then the column title would be 0.05. So 2.0 plus 0.05 will give us, you'll find this value there. Okay. Once we have this, we just plug everything into the formula to find the x value. So our mean was given in the problem. Our z-score we just found inside the table. We found the 0.98 inside the table and related that to a z-score of 2.05. And again, our standard deviation was also given. Okay? There, sorry. And so this corresponds, the score 130.75 which we would round to 131 because IQ scores are not given decimals. A score of 131 separates the upper 2% and the lower 98%. I thought there was going to be another statement there. Sorry for moving on fast. IQ scores are normally distributed with a mean of 100% and a standard deviation of 15. Find the IQ scores that separate the middle 90% of the scores from the top and bottom 5%. Okay. So now we have 5% on each end or on each tail. So 90% is what's left in the middle. So remember again, when we were trying to find the values between, we take the z-score for the upper value, which would be all the white area in the middle and this black tail to the left. And then we subtract the area from the z-score table of that lower value, because what we're doing then is we're finding just the white area, right? The area below x2 from table A2 is everything to the left, which would make this also white. And then we're going to subtract out that area so we only get what's between the two black tails. All right, try this one and see if you can do it. So we're first looking for an area. Be careful here. What is x2's area that we're going to be looking for? Well, if the area to the right is 0.05, the area to the left is not 0.90, it's 0.95. x2, because it's 90% in the white plus this 5, so x2 represents the area everything to the left, which would be 95 because there's 5% to the right. Okay, so again, we're going to find the area to the left of 95. That has a z-score of 1.645. When we look for the area in the table that's 0.05, we get a negative 1.645. And that's kind of what we'd expect, right? Because it's a symmetrical shape and we have symmetrical tails there. So we calculate the x values for each of those scores. And I-scores, I was talking about the area, but we needed to get these z-scores from that area. And then we can plug it into the formula and get to the two x values. So it's got to be between 75 rounding and 125. So IQ scores between 75 and 125 would represent the 90% of the scores from that's separate, the middle 90% of the scores. Again, your technology at the end of this text. Got great examples for Excel. I would look at both examples because you may use your calculator on the test. You may not have Excel for the tests. And then here's some more problems you can just work out. I'm not going to walk through these. So that's all that we covered for 6.1. It's been a long lecture. Hopefully you took a break there in the middle. I should have added a break. I'll try to remember to do that next time.